We ended basically saying that there were two formulations of optimal transport that were out there. So if you hear about Monge, it's this first problem which involves more like a map, and Kantorovich is more how to spread out the mass. So I had a very relevant question, which was, well, it seems that here the big difference between those two things is that when I describe Monge's problem, I didn't give the choice of the worker to do what people call to split mass. That is, if I grab mass at this point x, you take everything or nothing, right? And you bring it somewhere else. Here what Kantorovich introduced is more the idea that, well, things are somewhat divisible. You can split up this group into smaller groups, maybe 1 or 2 or 3, and then you do this mass splitting job of allocating the mass to different targets. So indeed, this is a defining difference between the two problems. In Monge, we are just really focusing on one-to-one mapping, whereas in Kantorovich, we are focusing on one-to-many possibly mappings. And this is a key feature. So let me just give a more mathematical formulation for all this. So in Monge's problem, we will be dealing not only with a real line, because that's a bit simplistic. Actually, Monge in his original work was already considering 2D as a space, which is of course very relevant for public works. In the more general case, let's say we have omega, a space that we can define probability distributions on, measures. We have a cost function. So again, this cost function doesn't need to be a distance. Actually, it could be, let's say, a distance to the power 2 or 3 or something that's just any cost that you can come up with between 2 points. And what we will be doing is find a map, T, that goes from the space to itself, that minimizes the cost. So the cost is, again, what I just said. It's the distance between x to T of x, as quantified as this cost. Then you weight this cost by the mass that you're actually moving, and then you integrate, and the constraint that you have is, again, this weird, I mean, if you're not familiar with it, constraint that the push forward of T, of mu under the action of T is equal to nu. Okay, so what you push and get in the end is what you wanted. So what you can see is that this is an optimization problem, but it's already a bit annoying, right? Because we have this constraint, and it's clearly not a constraint that we are familiar with. It's not something that's in that is in optimization textbooks. So let me just say that there was no progress on this problem for a long time. Surprisingly, Monge proposed this problem, and it was kind of under the radar for 1 or 2 centuries. Even Kantorovich, actually, when he rediscovered optimal transport in a different framework, didn't really know about Monge's work. And not much progress was done on this problem that Monge proposed until the 80s. So this is 1781 and this is 1987, 200 years later. And there was a big achievement which was obtained by an analyst, a mathematician, a French mathematician, Yann Brenier. He's actually at École Normale Supérieure right now in Paris. And he proved the following. He said, well, if the space that I'm dealing with is RD, okay, something we can all relate to, and the cost is the squared Euclidean distance, so it's the squared of a distance. So unlike Monge, Monge was dealing with, he first formulated it with distances, but here is the squared of the distance, which we all can relate to as well, because we all play with squared Euclidean distances in our machine learning models. Then there is this result which says, if the two distributions are roughly smooth, I mean, absolutely continuous with respect to a Lebesgue measure, so you can think of them as densities, then there is always a map that transports optimally this density to this density. And I can say something really interesting about it, which is that it must be the gradient of a convex function. So let's take a step back. A convex function is something that's defined on RD, which takes a vector as an input and outputs a number, okay? So f of x or u of x would be equal to some number. When you take the gradient of a function, what you get is something that takes as an input a vector and outputs a vector, right? It's the gradient of the function at that point. Well, it turns out that you can prove that the optimal transport between those two distributions in the Monge sense is the gradient exists, and it's necessarily the gradient of a convex function. And it's actually there is only one convex function up to addition of a constant factor that satisfies that it transports this measure to this measure. So once you find formulate all of this, if you give me a convex function whose gradient maps this measure to this measure, then I know it is the optimal transport. And I will show you that this plays a role actually in when you deal with Gaussians, if you want to transport between Gaussians. And I will show you this is also related to this Fresher inception distance that people used in GANs recently, which is about computing transport between Gaussians. So this is a beautiful mathematical result, which has a lot of other far-reaching extensions in PDEs. And it's usually one of the big chunks of biggest achievements that people attribute to transport in the last 20 years. But it's not going to be so important for us in machine learning. Can anyone guess why this is not always so relevant for us? I mean, not so useful? It could be useful, but only if you're interested in the more theoretical papers that appear at NeurIPS and less of the practical ones. Well, the thing is, here, for this result to be true, I have assumed that the distributions of mu and u are densities. And in machine learning, very often we don't have that. Very often what we have to deal with is Dirac masses. And in the Dirac mass setting, if one measure is a Dirac mass, usually there is no Monge map that maps this to anything else. So imagine there's no way I can take the push forward of a Dirac mass at this point and recover this nice smooth blue density. Why? Because if I take the push forward of this Dirac mass, the only thing I get is delta T of x, and I can only recreate, if you want, another Dirac mass. So the Monge problem is not well defined, yes?
Would there be, again, would there be any way to relax the Dirac mass into something that is more reminiscent of its density?
Excellent question. So this leads me to my next slide. And this is exactly what Kantorovich's idea is. It's the idea, well, the problem with Monge map is that indeed what we are considering is deterministic maps somewhat. I'm just telling you the worker needs to go at x and bring mass at t of x. There's no choice. Now, what would happen if we were allowing the worker to be a bit more loose, right? You can take the mass at x, but I'm not asking you to take all the mass that's at x. I'm going to ask you to distribute the mass that you found at x somewhere, which is a probability, which follows the shape of a probability, which would be like p of y given x equals x. Okay? So it would be more not a deterministic, but a probabilistic thinking, right? I mean, you could say it's a probabilistic thinking, but you could also just simply say that you're smoothing things out, as you just mentioned. I'm not going to put all the mass here at one point, but I just allowing you to somewhat distribute it. And if you do that, what you get is, instead of having a deterministic map, you get something that looks like a probabilistic map. And a very convenient way to parameterize those probabilistic maps would be a coupling. So what is a coupling? It's a probability distribution on the product space of omega times omega. And the constraint somewhat that if we transport the density of a measure mu to nu, we get what we want in both cases, is the marginal constraint. What we want is that we will consider for two mu and u's, for mu and u, all the couplings, all the joint probability distributions defined on omega times omega, such that P, this coupling, has the first marginal set to mu and the second marginal set to nu. So if this sounds a bit complicated, let me just show you this visually. Imagine my omega, my space omega is just R. Okay, it's just the real line. And so what I'm comparing are two distributions, two univariate distributions, okay, two densities on the real line. So what I am referring to when I'm talking about joint couplings with marginals which are prescribed is basically things that live in the square of R, okay, R times R, and our probability distributions. So the integral of this volume is equal to 1, just as this is equal to 1 and this is equal to 1. And now, if I marginalize, if I integrate with respect to this coordinate y, I get the distribution with respect to x. And if I integrate in this direction, I get this distribution here. So whenever you give me two probability distributions, I'm not going to consider all the set of maps that can push forward a measure to another. I'm going to consider all the couplings that have the marginals that are set on the left and on the right. So here there is an example of such a coupling. Here there is another one. Okay, so in general there's a lot of couplings, and there's at least always one coupling that satisfies this constraint. Can you think of which coupling it would be? If I give you a mu x and nu y, what coupling can you come up with, which the product? P of xy is equal to mu x nu y. Okay, and actually I think this is the coupling there. You're just taking, basically at each point here, you're just taking the product of these two things, and then you just make sure this is normalized if you were to do this in a finite grid here. But then you just take the product. Okay. When you have two random variables and you need to come up with a coupling between them, well, it's easy to just assume that those random variables are independent, and then you just have the coupling, the independent coupling. So in this case, there will always be a coupling that will couple those two distributions mu and nu. And that's the good thing, because this is where Kantorovich's point of view enters. Basically, instead of thinking about this mapping perspective, Kantorovich proposes something which is you could see it as a relaxation, which is to say, of course, instead of considering those maps T, I'm going to consider couplings P. And those couplings must be such that they have the right marginals mu and nu. And this is usually what people call the Kantorovich optimal transport problem, or the Primal optimal transport problem. Is there any question? Okay. I want you to keep in mind those illustrations that I gave you earlier. This is really the idea that the worker brings the mass from x to t of x, and this P coupling here is the matrix. Remember that I was looking for when I was saying this barrack must send that many soldiers to those front lines. Now, this problem, well, Kantorovich is famous for this problem, but I might have told you there were other people that actually had the same idea at the same time. It was not in this abstract formulation with double integrals. It was more like with sums. But Hitchcock also had this idea. Tolstoy also had this idea. What Kantorovich is rather famous for is for his so-called dual formulation. So the dual formulation is something that should remind you a bit more of what Arthur was talking about. So Arthur mentioned that Wasserstein distances were in the class of integral probability metrics. I think it's true if you restrict this to the Wasserstein 1 distance, so I will explain later why. But here you can start to see a bit of a flavor of what you saw with Arthur's course. This was an infimum over couplings. Maybe this is the first time you see this. Is a bit not necessarily something you're comfortable with, but this is a bit different. This is the supremum over functions phi and psi that you can integrate with respect to mu and nu. This is the meaning of this L1. And you're integrating, you're testing, as mathematicians would say, this measure mu against phi and measure nu against psi. And then you have this weird constraint. So Arthur was doing something a bit similar, but it was a bit more simple, if you remember. It was just saying a soup over f, where f is Lipschitz. You know, so f has something to, or f is an RHS ball or something. F must have some property that we can define, and you integrate the difference, the value of f against mu and or against nu. So it turns out that these two things are the same. Okay, the primal and dual problems of optimal transport, and Kantorovich is famous actually for introducing this duality first. So duality is a really fundamental aspect in mathematical programming, and we see it everywhere right now in of course in machine learning. So in duality, the principle in duality to me is to say that when you have an optimization problem in which you have constraints and variables here, and you have an objective here, okay. So here the set of the variables has a certain size. Here it's of the order of omega times omega, okay, omega square. And the constraints that I want omega to fulfill here are just of the size of omega. It's basically, if I integrate mu then I will get p, I get mu. If I integrate p, I get nu. And then here in the dual, you're kind of taking you're reversing perspective, and you're saying that if you had a few constraints here, they will appear here in the variables, in the objective. And if you have a few variables here in the objective, they will appear here as the constraints. I will be more clear about this later. Let me just give you a derivation of duality, which is a bit more self-contained. So I'm going to take this notation here. For two functions psi and psi, this plus round operator is essentially the function applied to the first variable and the second function applied to the second variable, okay? So it's like a tensor sum. Now, let's try to derive Kantorovich duality. So I'm going to introduce an object which is a bit complicated, but which does the following job. It basically says it's a function of P, those couplings, which will be 0 if the coupling has the right marginals, and it will be plus infinity if it doesn't have the right marginals. So remember, the marginals is the idea that if you have a coupling, if I integrate with respect to one variable, I get the good marginal, and if I integrate with respect to the other variable, I get the good marginal. And why does this weird function here does exactly that job? Well, imagine that I'm taking the supremum of phi d mu plus psi d nu. I am allowing myself to take any functions. And then I'm subtracting to this the sum of phi plus psi on p, on this coupling p. Well, if you do that, you would get a quantity. Let me see if I have this in my slides. No, I didn't see it, put it in my slides. It's because I assumed it would be obvious. But if you think a bit about this, you're taking any function phi. This function phi can be anything you want, and you want this to be very large. So you're going to integrate phi against mu. You want it to be very big. But then you're subtracting the integration of phi against p. And this will here you would only see the marginal, the first marginal of p appear. And you're going to integrate psi against nu. But here you're going to subtract the integral of psi here against the second marginal of p. So if these two things cancel out, then this is equal to 0. There's nothing to say. And this will only cancel out if p has the same marginals of mu and nu. If it doesn't cancel out, then it's plus infinity. Because there is always a way that we find to define the phi or a psi that makes this thing blow up, right? Okay? So this is just an identity that tells me if you take a supremum of those functions, this will necessarily blow up if p doesn't have the right marginals, and will be 0 if p has the right marginals. And so how would I use this? Well, a standard trick in optimization is to say that if you have a problem which has a constraint, it's the same thing as removing the constraint, but adding it here as this indicator function. Okay? So I'm saying I'm going to minimize against for couplings that have the right marginals. And here I'm saying I'm going to minimize any positive measure on this space. It doesn't need to have the right marginals, except there's a bit caveat. This is plus infinity if the coupling has the right marginals, and it's 0 otherwise. So by definition, if I'm minimizing, I can't afford to consider any p that has a plus infinity value there. Okay, so it's a bit of just rewriting things, but you will see that it makes things a bit easier for duality. Okay, so now I'm going to consider this problem. This was the Kantorovich problem, except that I have transferred the constraint here to this indicator function. So let me just lay out this optimization. I'm saying I want to compute the infimum over all the p's of the cost plus something. You remember this IP of p here was the supremum over any functions phi and psi of this quantity. Okay. Remember, this blows up if p doesn't have the right marginals. It stays at 0 because it cancels out if p has the right marginals. So now I'm going to play a bit of a game of inverting things. And this is the big game in duality. First, it doesn't hurt if I put the soup that I had here behind. Okay? So I have this big term that encapsulates both the integration, the optimization with respect to p, and both the optimization with respect to phi and psi. Now, I'm going to rearrange my terms a bit. Okay? What I just did was just bring this here, and then I'm rearranging them so that all the terms in P appear here on the left, and all the terms in phi m psi only appear on the right. Now, what I can do is the following. I need to be a bit closer. I'm just going to say that here I had an integral with respect to P and an integral with respect to P. I'm just basically pulling them together. And I'm integrating P against C minus this phi plus psi, okay? And now I'm going to do something that I should be justifying a bit more. This is where duality proofs usually require a theorem that I don't have the time to prove now, but which is basically, it's fine actually to do this sup inf inversion. So what do we get here? If I do this sup inf inversion, it's basically that I'm considering first the integration with respect to P, and then I will see what happens with respect to phi m psi. And if I do that, well, think about this. I am taking the infimum over any coupling, any measure, defined on omega square, of this C minus phi plus psi. So this is a function of two arguments, right? C of xy minus phi of x plus psi of y. How small can this be? Well, this, imagine all of those terms, cxy minus phi x plus psi y, are positive. Imagine all of this is or non-negative. If you're integrating a function which is non-negative against a probability distribution here, which is necessarily something that is positive, then the best thing you can do is 0. And that's the case if all of this is positive, right? Imagine that for a second, one of the values of this function becomes negative. If it's negative, then I just need to put an infinite mass on that value to get something that will become minus infinity. So what we get is that this here function is actually something that looks like an indicator function, but for another set of constraints. And it basically is something which is 0 if this is positive. Again, I'm repeating myself, but if you're taking the infimum over many distributions which are by nature non-negative, and this is always non-negative, then this can only be, then the best thing you can do is 0, and you set P to 0. If, on the other hand, this sometimes is allowed to be negative, if there is a value, just one xy for which this is negative, then I would put a huge mass on that point, and I would get something that goes to minus infinity. So this is, again, a indicator function for this constraint set. So I'm sorry if this is going a bit fast, but the main idea is write those constraints as indicator functions of some proper set of test functions, and then massage a bit this equation. And so what you get here is the following. If this here is 0 when I have this constraint, and it's minus infinity when this constraint is not observed, then it means that I can actually only focus on those phi's and psi's for which this is always positive. And this is the meaning of this. Okay? So if you want to take time and look a bit more at the slides, they are available on my website. But here, this is a very standard duality argument in which you take this primal problem, take the constraint as formulated as this soup, and then invert, and then get this. So the dual optimal transport problem is this problem which doesn't have so much of this easier interpretation in terms of Kantorovich, but it's essentially considering test functions, phi and psi, that you integrate against the first measure and the second measure. And those test functions must be linked by something there, which is that phi of x plus psi of y is smaller than the cost between x and y. Okay? Now, if you've heard about Wasserstein distances and Wasserstein-Gann, it's because usually in the literature, when this cost function is a distance to the power something, to the power p, then we call this a Wasserstein distance between two probability distributions. Okay? So this is really the equation that I used earlier. The only thing that I did is substitute the cost of xy by this distance between xy to the power p. So if p equals 1, you will recognize exactly basically what Monge what Monge was trying to solve. How can I compare two distributions if the cost is just the distance between of the travel? If p equals 2, as you should expect, in math, very often when we use squared Euclidean distance and not Euclidean distances, things work out a lot better, right? I mean, in orthogonal least squares, we use squares for a reason, right? Which is that things are easy to differentiate. Mathematically, it's easier to. There are a lot of closed forms. So in optimal transport, you will often see this WP, Wasserstein P, and sometimes people will say, okay, I'm interested in the Wasserstein 1, so P equals 1. I'm interested in Wasserstein 2, P equals 2, square Euclidean distance. And then, not surprisingly, there's a very different variety of results that you can get out of those, out of the choice of whether P is equal to 1, 1.5, or 2. Mathematically, it's easier to deal with P equals 2. In applications, very often P equals 1 is actually very relevant because, again, square Euclidean distances tend to be very sensitive to outliers, whereas the Euclidean distance itself, P equals 1, is a bit more robust. So there's a bit of an interplay between those two. So very often to remove this 1 over P here, we use this notation WPP, which is the Wasserstein of order P to the power P. Just like in a Q norm, we use very often the Q norm to the power Q. Now, there's one thing that I wanted to mention, which is that if you look at this problem compared to the original optimal transport problem, the dual problem, it is a bit, there is a bit more of I mean, it looks more like an integral probability metric in the sense that we're integrating these measures against those test functions. And somewhat it seems less daunting a task to integrate, to compute these integrals than to compute this double integral with the coupling, right? But the difficulty has not really disappeared in the sense that this omega square size of the size of the problem is actually hidden in this constraint. We have now that even though this is of size omega, this is still of size omega square. We need that phi and psi agree so that phi of x plus psi of y is smaller than d of x y to the power p. So Kantorovich duality proposes this slightly different perspective. But if you actually keep on working on this, and this is an interest of optimization, you can try to get this problem to be a bit better behaved, better defined. Well, there are some techniques that have been proposed and which are very, should remind you of a lot of things that you might have seen in convex optimization theory, like Legendre transforms and things like that. So let me try to walk you through this. So imagine you want to solve this problem. Okay, you want to find a function phi and a function psi, such that if you integrate them respectively with respect to mu and nu, but you need that phi of x plus psi of y is smaller than the distance between x and y. What could you do? How could you try to address this problem? Well, suppose that I give you a function phi, okay? Phi is more or less fixed, and I ask you to play with psi. What kind of function psi can you come up with? Well, there's a simple game that you can try to do. It is the following. Well, we need a function psi here that satisfies this constraint. If phi is fixed, if frozen, I need that psi satisfies always this constraint. And I want to find the best psi to maximize this. Well, this constraint, if I reorder it by putting psi here in the beginning, I just need that the function psi satisfies this for every couple of pair of points, x and y. Okay? So what does that mean that I want this to satisfy this constraint for every pair of points, x and y? Well, it's very natural to write it in this way. If this is true for every pair x and y, in particular, I mean, it's equivalent as saying that it is true for the infimum over all x's of this. If the infimum of all x's of this quantity is bigger than psi y, then this is true, of course, right? So this is equivalent. So I want a function psi which is smaller than the infimum over all x of this thing. So I'm playing here with two variables x and y, so you have to be a bit careful. Now, here, by defining this infimum, I'm actually defining a function of y. Imagine I give you a y, you compute this. I could very well define this to be my function of my function psi. And this is what we call phi bar of y. Okay? It's for every x, for every y, it's the best, smallest thing you can get by looking at all x's of this difference between two distances, distance and phi of x. So if you give me phi, I can produce a function of y. So phi is a function of x. I can produce a function of y that will have this property. And if you think about it, it's the best thing that I can do, because my interest is to make this function psi as big as I can, to make this sum as big as I can, because this is a positive measure. And so if this is the constraint that I have, and I want psi to be as big as it can, well, I might as well justify it to be exactly that, right? Psi must be smaller than this thing, so let it just be this thing, if I want it to be just very large. And you can very easily prove that you cannot do better. So if you give me a function phi, I cannot get a better other dual potential, people call this a dual potential, than this function here. Now, what you can do is just simply consider, okay, if you told me that for a given phi, I cannot get something better for psi than this function, I might as well rephrase this problem as supermem of phi of this first term, which doesn't change, and this second term here is just substituted by phi bar. Okay? But now you could think, but what about doing this twice? Okay, I did this, I started with a red function. I gave you the best blue function that I can get. Now, maybe what I could do is do the other way around. I give you a blue function, can I get a good red function? And the good red function would be, again, the same thing, like the symmetric of this. It would be the infimum over all y's of the distance between x, y minus psi of y. If you give me a blue, I can get a red. So then you can start playing with this, right? I start with a red function, I get a blue function, with that blue function I get a new red function, etc., etc. And then you could go on forever like this. Unfortunately, it doesn't really work, in the sense that after 2 iterations of this, I get a blue function out of a red, I get a red out of a blue, etc. You can very easily prove that this is the same. So after 2 iterations of this game, you just stop. However, what this gives you is a language to define those potentials that you can be interested in. And this is where I'm saying that this is really a generalization of convexity and of Legendre transforms. If you're familiar with Legendre transforms, you've already seen this kind of little game of playing an inf over the distance between 2 points squared Euclidean minus phi of x, or the soup with respect to the dot product. Here I'm slightly generalizing this by saying that what I will be considering is just functions which already have undergone this kind of process of alternating between red and blue to get this formulation. I'm just saying basically I am going to optimize over functions, red functions, which are themselves the transform of some blue function, and then add the blue function that I get out of this red function. Okay, so this is usually the more advanced optimal transport formulation that you find appearing increasingly frequently in all those GAN papers. Okay, the C transforms, etc. Now, here is why I can say something about what Arthur was mentioning, about the Wasserstein distance being the supermem of a difference of the integral of f d mu minus the integral of f d nu over Lipschitz functions. So again, remember, Arthur was saying integral probability metrics are these things where you integrate the difference of 2 measures against a test function, and the test function must be in some RKHS ball, a Lipschitz ball, or anything. And he said, if it's a Lipschitz ball, then it's Wasserstein. Well, it's true because of the following thing. If the cost is indeed a distance, just a distance, so p equals 1, then the fact that I can limit myself to functions that are the transform of some, have this property that they are the transform of some blue function, is the same thing as saying that they are Lipschitz. And this transform, the blue transform, is itself minus the red function. So it's relatively basic math, but I think I'm going to skip it because I think you're still a bit, you're still digesting. So if you're interested in this proof for reference, you can look at the slides. But I find it interesting that you are aware of this because a lot of papers right now in this Wasserstein / GAN literature work a lot on this idea that Wasserstein 1 is the same thing as integrating against Lipschitz functions, but nobody really explains why. And if you need to go and look for reference, either you can go to Villani or in our book, but there is a reason why this doesn't come out of nowhere. Okay, let me just restate what I just said differently. People will define this Wasserstein distance to you as this integral of the best coupling, and then somewhere from out of nowhere, someone will say, "Ah, but Wasserstein distance is actually this integral probability metric on the space of Lipschitz functions." There is actually a link between those two things, a rigorous one, and you can actually make this connection. So, just to skip this proof, basically the Wasserstein one. So this is really actually Monge's problem. You can write it as the supremum over Lipschitz functions of the difference between mu and u. Okay, and only in that case, and in that case only, do you get this family of integral probability metrics that was mentioned by Arthur. If you're not considering a cost which is a distance to power p equals 1, then you're not, the Wasserstein distances are not integral probability metrics. They're more general than that. So let me just watch the time. So on the one hand, I've been playing a bit with those two formulations of optimal transport, the Monge and the Kantorovich. So Monge was this interest in the maps, and Kantorovich was, let's be a bit more general than that. Let's relax things. Instead of having maps, we're going to have probabilistic maps. So a natural question that you can ask is, what about what's going on with this relaxation? Is it tight? So in optimization, this is how you would define it. First, I was interested in things which were maps. Then I relaxed this to be, well, the map doesn't necessarily need to map to one point, but it can map to a hill. When I optimize, do I get the same thing? Okay, and this is something that has been in the mind of mathematicians for a long time. And let me just roughly say that yes, it's more or less the same thing when you have densities. When you have densities, actually solving this optimal transport problem with the Monge perspective is the same thing as solving it with the Kantorovich perspective, in the sense that you will get an optimal coupling P star, which will be something like identity, so X maps to X, and T star, which is this mapping. So in other words, I think I will show you a plot later, what the optimal coupling looks like. You remember earlier in the slides, I showed you a few couplings trying to give you a sense of what it looks like to have a coupling between two measures. Well, if you were to solve exactly the Monge problem, the coupling that you would get is not something that looks like this. It's just like a ridge that to a point X associates only a point Y. So the coupling is very degenerate in the sense that there's very little randomness involved. And then if you actually were to solve exactly the Kantorovich problem with two nice smooth-looking densities, you would recover exactly that thing. But let me just skip this because this is of interest mostly for mathematicians, and it's just to make the link between these two things. So, so let's go back a bit more to visual interpretation and an idea of what's going on with optimal transport. I have defined a few mathematical quantities, a bit hardcore. Now let's just go back to something that's a bit visually more appealing. When you define a distance between distributions, between anything, if I define a distance between this point and this point, I'm not only giving you a quantity, but often cases I'm also giving you a way to interpolate between things. I'm giving you a way to say, well, if the distance between this point and that point is, let's say, 7, there is a shortest path between those points whose total length is 7. And then I can try to visualize what this path looks like. Might be of interest. So in this case, imagine that you have this probability distribution. This is a mixture of Gaussians and another mixture of Gaussians. And what I told you is essentially I now have this is a set of all probability distributions, and I have a nice metric, a new definition for a metric between distributions. And this is what the length of the path connecting them looks like. What is relevant, though, and has been increasingly used in recent years, is that this also defines this path, okay? And the path is actually a succession of probability distributions. And what you can see in this path is you can very clearly see that there is a transport. right? The mass, which is here, kind of starts moving in a coordinated way from this measure to this measure. So let me try to give you an insight of why this is new and what's different. So imagine that I have two probability distributions. So let's say this one, the blue one, so it's a Gaussian, and here it's a mixture of two Gaussians, okay? So I have two probability distributions. If I ask you to compute, for instance, the average or the interpolation between those two distributions, well, what you might do is just simply take one distribution, take the other distribution, add them, and divide by 2. That's the average, the way we do it. I mean, the usual average. And what do you get in that case? Well, here I've drawn the entire interpolation, so maybe it was a bit too much. But what you would get as an average is basically this. Okay? Now, if you were to do the average or the interpolation in a Wasserstein sense, and I will explain a bit later how you can do that, this is what you get. Okay? And this is a completely different geometry. Because here you can see that we never really used the geometry of the real line to compute those interpolations. The only thing, you give me two measures on any space, and you ask me to compute their average, and we'll just do first measure plus second measure divided by 2. That's all. This could be supported on a manifold of any kind or anything. Here, in the Wasserstein case, what I did is actually to go from this distribution to this distribution, instead of playing this elevator game, you know, where I damp down the value of the first measure and increase the value of the second measure, and I do like this, I'm actually going to look at how I can go from this one to this one in the way Monge would basically recommend to do things, right? And that is slowly moving, gliding from one measure to the other. And you can see that in some applications, both things could make sense. Imagine this is like, for instance, the histogram of some temperatures that is given to you by a sensor, and this is the histogram of temperatures given to you by another sensor. And you want to make a fusion of those two measurements. What would you trust? Is it more like, oh, I want to keep intact the kind of variety that you give me, and so I'm going to have something that's very spread out? Or do I want to average things in a way that is more geometrically meaningful? And depending on the applications, this makes more sense. And you can imagine, of course, that it will make sense, especially in anything that's like 2D or 3D, like shapes or geometry. And we see this a lot in applications to graphics. So this is an image taken from a graphics paper in which we try to think, okay, I gave you this nice interpolation between two univariate distributions. Let's try to do this in 3D. Here a distribution will be a uniform distribution on the volume, so it's full inside and empty outside. And then I ask, what is the interpolation that you could come up with Wasserstein sense? Okay, all of the barycenters that I could get. I will define this more rigorously, but how can I go from those shapes or mix those three shapes together? And actually, if you do this Wasserstein mixing, you get something that's kind of surprisingly coherent. It's like a shape that's moving around. And of course, there's a lot of ways to interpolate between shapes. That's a very long-standing problem in graphics. But what is actually quite interesting is that we've taken a tool that was designed by mathematicians here. We've almost applied it as it is and checked what it looked like, and it gives a nice type of interpolation. We haven't assumed anything about the shapes, about the regularity of the shapes or anything. What we get is just this. It's just a plug thing we plug, and we get that. Of course, there's a lot of computations involved here that we'll be defining later. But we have a lot of examples like this where we have some interpolations between measures. And again, let me insist on the fact that this is not something that you would get out of your intuitive idea of what an average is. An average for us is just this plus this divided by this. And it's not this that we get. Here we're doing the averages in the Wasserstein space. So to conclude, because I think I have until a bit, 5 minutes, right? So to conclude a bit the first part of this presentation, let me just tell you that this idea of Wasserstein distances was something that mathematicians were excited about, especially in the last 20 years. So this is demonstrated by the 2 Fields medal that the field has received. Computationally, there were some things that appear a bit daunting. It was very difficult to actually even just compute optimal transport. I will explain this later tomorrow, because all of this business of computing optimal couplings with those constraints, or computing those potentials with this and that constraint, actually translated into pretty heavy computation. So up to, let's say, 2010, people in the community in machine learning and computer vision were using those tools, but always with the caveat that they knew that they would not scale. So in the computer vision world, these ideas of optimal transport suddenly became very famous in the early 2000s. People call them the earth movers distances, and they were fashionable for a while. But then after some time, people understood they were just too costly to actually be of any use. What has happened in the last couple of years is that we've found more efficient ways to compute or approximate optimal transport. And for me, this is a typical pattern that you find, which is that mathematicians think of bright ideas, and in an idealized world where they manipulate densities, and what they want is essentially to prove theorems. And people that are more on the applied side might be willing to trade a bit of that beauty for something that is maybe a bit more robust, maybe a bit faster, and that scales better. This doesn't mean that the two fields can't communicate, of course, it's the contrary. But I think it's an interesting perspective to see ourselves as, people that take those ideas from math, but kind of adapt them to what we really want. And what we really want is something that scales, that is robust, and that even if, for instance, your data is corrupted and the distance, you don't really know what the distance is really like, it will still return something that's useful. And what we've seen in the last years now is that instead of using this distance as just something to measure how far two probability distributions are, we're using it now as a loss function. So a lot of machine learning is essentially trying to minimize the loss function. It might be of your prediction. So imagine now that you predict probability distributions. What you are producing is a probability distribution. The typical example is the GAN. In the GAN, the output of your machine is eventually a probability distribution. Now, what's going on in optimal transport is that instead of trying to focus on computing the distance itself, what we want to do is minimize that distance. Minimize this Wasserstein distance between what your GAN produces to the real data. And we're seeing this also in graphics. If you want to produce a shape, maybe you want to minimize the distance between the shape you're producing, the Wasserstein distance between the shape you're producing, and your ground truth, etc., etc. So I will be talking a bit more about the family of tools that allow us to do this. So instead of just focusing on the distance, we will be focusing on minimizing the distances, Wasserstein distances, and as you can guess, what this involves typically is computing some form of gradient of the distance with respect to one of the two variables. So I'll continue tomorrow. Thank you very much for your attention.